Nature smiles in color. Lee Hunt.
Boring.
Two faces stare at you. One on the left, one on the right. Which is more attractive? You've already answered in a split second. And guess what? Most people would agree with you. Biologist Randy Thornhill and psychologist Stephen Gangestad found a simple rule. The more symmetrical the face, the more attractive we think it is. Here's the crazy part. Your brain is a fucking accurate symmetry checker. It immediately measures how one side of the face lines up with the other. But wait, there's more. Langlois and Rogman took a bunch of faces, averaged them into a single composite, and found people rated that average face more attractive than most of the originals. Why? Averaging erases imperfections, smoothing out asymmetries. And crucially, this is a universal phenomenon. Doesn't matter your culture, age, or occupation. MRI scans show that when we see symmetrical faces, our brain's pleasure centers light up. The same areas that respond to delicious pizza or good tunes. Evolutionarily, it's no shocker. Symmetry hints at health, robust genes, a better chance at survival. Humans love symmetry. Want to know who else loves it? Nature itself. According to physicists, the entire universe is hooked on symmetry. But what does that even mean? Picture a perfect sphere. Spin it any way you like. It never changes. That's rotational symmetry. Or think of an infinite rope. Shift along it, and the pattern stays the same. That's translational symmetry. Our universe works similarly. Imagine lobbing a ball out into the void. It flies in a straight line at constant velocity. Move to another spot, do it again. Same result. The laws of physics don't give a shit where you are. Ditto for time. Fling the ball now or in an hour, the result doesn't change. Nature's not fussy. Same deal. Spin yourself around, you'll find the same physics waiting. Then along came Emmy Noether, one of history's greatest mathematicians. She proved that every symmetry spawns a conservation law. If physics doesn't change when you shift in space, momentum is conserved. If physics doesn't change over time, energy is conserved. If it doesn't change when you rotate, angular momentum is conserved. So that's why a tossed ball keeps going in a straight line, or why a spinning top keeps spinning. It's all about the underlying symmetry. Even Newton's classic action equals reaction is just space symmetry wearing a fancy hat. A starship rocket blasts upward by shooting exhaust downward, riding on that symmetrical principle. But hold up, the real universe is trickier. It's expanding, so time symmetry breaks. A photon trekking across billions of years loses energy, its wavelength stretching as space grows. Why does any of this matter? Because these symmetries are the blueprint for fundamental laws: conservation of energy, momentum, electric charge, you name it. These aren't random cosmic guidelines, they're direct outcomes of the universe's hunger for mathematical beauty. Nature demands that elegance, and from that demand, we get all the physics we know. Yet a paradox lurks. Picture a ball in a spinning centrifuge. From outside, it's doing circles. From inside, it seems like some mysterious force is pushing it into the wall. How do we reconcile these views? It's like measuring an airplane's altitude. If you measure from sea level, the plane moves straight. But if your map is the bumpy Earth's surface, that path looks curved. The plane's flight hasn't changed. Your point of reference has. Physicists cheated their way out of this problem by adding special forces. In a centrifuge, it's centrifugal force. In gravity, we call it curved spacetime. The moral of the story? Even illusions can be pinned on deeper symmetries, and nature's quiet, stubborn insistence on beauty. It's like nature's inventing new stuff just to keep symmetry alive. And that gets seriously interesting when we zoom in on elementary particles. Think of that airplane example. We had to tack on an imaginary force field to explain its motion in different frames. Guess what? All of particle physics runs on the same principle. Check out electrons. Their quantum field has a certain symmetry. You can tweak its math in a uniform way everywhere, and physics stays the same. But if you try messing with it differently in different spots, the laws of physics start crashing. Nature's fix? It conjures a new field, the electromagnetic field, giving us photons, the building blocks of light. Boom. That's why light exists. That's why you feel electrostatic repulsion and don't plummet through your chair. Same with space-time. For physics to stay consistent for every observer, space must bend and warp. General relativity and gravity were born from nature's stubborn insistence on symmetry. And that principle was so unstoppable, it unraveled some of matter's biggest secrets. From symmetrical clues, physicists found out protons and neutrons are made up of 3 smaller particles, quarks. That 3 is no accident. It's tied to a specific symmetry. It doesn't stop there. Flip the direction a particle travels in space-time and switch the sign of its charge, you get an antiparticle. Like antimatter is ordinary matter going backward in time. Then there's supersymmetry, a possibility that pairs matter particles with force-carrying particles. It's like the universe is playing this cosmic chess game, pairing everything up in an elegant dance. All from a simple math concept turned into a universal skeleton key for how the world works. This video is based on the books of Nobel Prize-winning physicist Frank Wilczek, especially A Beautiful Question. If you think this video is good, the book will blow your mind. In it, you'll find how music hides inside atoms, why your fridge magnet is stronger than Earth, why physicists chased the God particle, which equation turned out to be smarter than us, how to catch infinity in a drawing, and why physicists envy spiders. Remember, hitting like and subscribe helps new videos keep coming. Now, let's rewind to Pythagoras. In his day, nobody saw him as a mathematician or scientist. He was a spiritual leader, a miracle worker, founder of a downright secret cult in southern Italy. These Pythagoreans built a freaky intellectual mysticism around worshipping numbers and musical harmony, calling them the keys to the universe. Their core idea, that number is the essence of all things, turned science on its head. And scientists still rule with that approach today. Legend says that when Pythagoras discovered his famous theorem, he was so shocked he broke his own vegetarian rules and sacrificed 100 bulls to the gods. Why the freakout? Because he found a mind-boggling tie between shapes and numbers. Take a right-angled triangle, build a square on each side. It turns out the biggest square's area equals the sum of the smaller ones. Done. That's the Pythagorean theorem. There are countless ways to prove it, and each proof spotlights a new angle of the same truth. Geometric shapes follow numeric laws, and for the first time, it was crystal clear that math can describe physical reality. That's the real magic of mathematics. The same truth can be glimpsed from infinite angles, each revealing yet another facet of its haunting beauty. Pythagoras' so-called simple theorem cuts deeper than you might think. It reveals a hidden link between form and number, between what we see and the invisible order beneath. Ironically, that same theorem, leading Pythagoras to proclaim everything is a number, ended up debunking that statement. The story goes like this. Pythagoras' student Hippus looked at an isosceles right triangle, 2 cathetas the same length, and by applying Pythagoras' theorem, found the square of the hypotenuse is twice the catheta squared. Easy stuff, until Hippus tried to find integer lengths that satisfy this. Spoiler, it's impossible. No matter which integers you pick, the numbers don't add up. Hippus basically showed that not everything can be expressed by tidy whole numbers. This was a crippling blow to Pythagoras' worldview, revealing that nature doesn't just speak the language of integers, it also speaks geometry, and now, as we know, even quantum logic. The consequence, Hippus mysteriously drowned at sea soon after. Coincidence? You decide. Watching musical strings, Pythagoras stumbled on 2 more breakthroughs. He realized any stringed instrument, from ancient lyre to modern violin, basically works the same way. A stretched string vibrates, producing sound. While that sound can be influenced by a million factors, Pythagoras spotted something huge. 2 basic parameters, the length of the vibrating portion and the tension in the string, determine which notes come out. If you have 2 equally tensioned strings with lengths that form simple integer ratios, they sound amazing together. Have 1 string to get a pure octave, the cleanest, sweetest interval out there. Ratios of 2 to 3 yield a perfect fifth, 3 to 4 a perfect fourth, and every musician from Bach to Metallica depends on these integer relationships. Every time they press a finger on a fret, They're unknowingly channeling Pythagoras' law. Second discovery, tension. Pythagoras realized if you weigh strings differently, thus changing tension, you get different notes. But here's the kicker. They only form sweet intervals if the tension is squared, as prime numbers. For instance, quadruple the tension on one string compared to another, and you get the same effect as if that string were half as long, an octave. This is more mind-blowing than the first, because the link between tension and musical harmony isn't obvious until you square the numbers. Now we've connected shape, size, weight, and sonic beauty in one numeric system. Pythagoras' theorem about right triangles plus his 2 rules for musical harmony ties it all together, building the foundation of an entire worldview that says math is the language of the universe. But what does it all mean exactly? Why do certain notes sound divine while others make your skin crawl? We still don't fully know. Sure, physics of sound is pretty advanced, but the mystery of musical beauty remains elusive. The best we can do is track how vibrations move from string to instrument to air to eardrum, carrying the same frequency all the way. Finally, deep in the cochlea, in your inner ear, a specialized membrane that responds to various frequencies sends electric signals to brain cells, each tuned to a particular note. And the real party starts when 2 notes come together. If their frequencies are in a neat integer ratio, like one is exactly double the other, your brain easily spots the pattern and goes, "Ooh, yeah, that's nice." We call that harmony. But if they're almost but not quite matching, the brain tries to pin down a pattern and repeatedly fails, giving you that nails-on-a-chalkboard dissonance. Listen to 2 neighboring piano keys clashing, and you'll know exactly what that means. Among the endless geometric shapes out there, a few stand apart like VIP guests, the Platonic solids. If you want to appreciate their special charm, start with simpler 2D forms. Regular polygons. Picture shapes where all sides and angles match. A perfect equilateral triangle, a square, a pentagon, hexagon, and on, theoretically to infinity. These pure shapes are like geometry's atoms, the essential building blocks of countless intricate patterns. They've seduced artists and mathematicians for ages. Just look at Albrecht Dürer, who stuck a cryptic polyhedron in his engraving Melancholia 1 as if to say, "Hey, isn't this mesmerizing?" Step up from polygons to 3D territory, and something mind-blowing happens. Instead of infinite possibilities, there are only 5 perfect bodies in 3-dimensional space, the Platonic solids. Why so few? Because you can only jam so many identical faces around a single vertex without them flattening out or gapping awkwardly. For instance, 6 equilateral triangles around a point lie flush in a plane like floor tiles. They never form a proper solid. That limit of 5 ideal shapes stunned ancient philosophers, Plato included, who felt these forms must in some profound sense mirror the universe's hidden architecture. Never mind that viruses, microorganisms, and bizarre little radiolaria skeletons were rocking these shapes eons before humans noticed. Nature loves them for their stability and efficiency. Plato also gifted the world with one of its most powerful metaphors. People chained in a cave, staring only at shadows on a wall, clueless there's a bigger reality behind them. Then Socrates basically says, "Yeah, that's us." Maybe what we call the real world is just a flickering projection of something grander. Physicist Niels Bohr adored paradoxical ideas like that, calling them deep truths, the kind that remain true even if you flip them on their heads. Maybe the universe isn't built on math, and that's true, but also maybe it is, and that's true too. Salvador Dali snuck Plato's dodecahedron into his painting The Sacrament of the Last Supper, playing up exactly this duality. So Plato actually fused 2 concepts. First, swiping from Pythagoras, the world's underpinned by numbers and musical harmony. Second, his own take on why reality morphs over time. He pitched a theory of an eternal world of perfect forms, and the messy mortal realm we see is just a sloppy imitation of those cosmic ideals. Imagine a perfect cat, never aging, never getting sick, while every real cat you've met is just an imperfect reflection of that archetype. Turns out modern quantum mechanics says something freakishly similar. Change might be a superficial phenomenon, while the deep layers of reality stay the same. Plato thought there were two ways to glimpse that ultimate reality: turn inward with philosophy to purge illusions, or study nature's laws. Which route did he pick? He doubled down on beauty, even if it meant ditching strict accuracy. If observations trashed his elegant theory, well, tough luck for the observations. When the Renaissance folks rediscovered Plato's ideas, they brought their own spin. They hunted for the ideal without trashing reality. Back then, artists had a gnarly challenge: how to paint a 3D world onto a flat canvas. No cameras in those days, and the rich wanted paintings that actually resembled themselves in their shiny trinkets, in fine detail. Here's the kicker. Once you really grasp how objects look from different angles, you see what truly matters about them and what's just fluff. It's like you're using your subjective eye in an objective way. Suddenly you're capturing the essence of things. Let's say you're painting a plain old landscape, a flat horizontal ground and a vertical canvas. Draw lines from ground points up to your eye, and something magical happens. The further a point on the ground is, the higher it shows up on the canvas. Meanwhile, the farthest points line up on a single line, the horizon. Welcome to infinity. This horizon line isn't real in the physical sense. It's the limit of your vision. But in a painting, it's literally there, quite real. And if there are parallel lines on that ground, on your canvas they converge to a single vanishing point on the horizon. Each set of parallels gets its own vanishing point, but they all share that horizon line. Enter Filippo Brunelleschi, Renaissance painter, who turned these observations into a full-blown technique. He even did this jaw-dropping experiment. He painted Florence's baptistery so precisely that onlookers could compare his painting to the actual building via a mirror. Mind blown. This single stunt jump-started a revolution in painting, mathematical precision powering art. Perspective is downright magical, especially when you create it yourself. Try this simple exercise. Paint a long hallway of square tiles. Start with one square near the bottom of your sheet, then draw a horizon at the top. Soon you'll see, not just the sides of your squares, but even the diagonals must obey the laws of perspective, each line racing toward its vanishing point. Following those lines carefully, you can build the entire grid step by step until you have a tiled floor that looks absolutely real. Every square is shaped differently, but your brain sees them as if they're all identical. Once you realize how perspective works, you start seeing those converging lines everywhere. City streets, railroad tracks. It's like escaping Plato's cave. But perspective wasn't just an art hack. It planted seeds that later blossomed into modern physics. Think about relativity. In projective geometry, that's just the idea that the same scene can be drawn from different vantage points. The pictures look different, but represent the same scene, just from various angles. Tied to that is the notion of symmetry. Spin an object around, and from a particular viewpoint it looks different, but overall it's still the same object in every possible orientation. That's change without change, in a nutshell. Then there's invariance, the flip side of relativity. Some things stay put no matter the viewpoint. A straight line remains straight, for example, or if three lines intersect at one point in reality, they'll do so in any accurate drawing, no matter how the angles shift. Finally, the strangest concept, complementarity. In the quantum realm, it means you can't measure all properties at once. Want to see where an electron is? You shine light on it. But that changes its momentum, so you pick which property you want to measure, and the other one's accuracy takes a hit. It's as if in painting you can't paint the same object from different angles. Quantum cubism is impossible. This great ideas, relativity, symmetry, invariance, additionality, combine at the heart of modern physics. They should also be at the center of modern philosophy and religion, but that is not yet the case. In all these contexts, they sometimes appear in alien and abstract forms that can be confusing. In such a situation, go back to projective geometry and you can see them embodied again in tangible, beautiful artistic images. The scientific revolution of the 16th and 17th centuries flipped our world upside down. Its crowning gem? A new method of digging for truth, best articulated by Isaac Newton, who called it analysis and synthesis. First, you tear a complex phenomenon into its simplest pieces. That's analysis. Then you rebuild those pieces into a cohesive understanding. That's synthesis. Newton raised the bar for science. A theory has to accurately describe reality, or it's just a shot in the dark. To explain the whole of nature is too difficult a task for one man, or even for any single age. It is better to do a little, but with certainty, and leave the rest to others, to those who will come after you, than to explain everything by making assumptions and being sure of nothing. For all his obsession with precision, Newton was also bursting with curiosity. His notebooks are jammed with speculations, from chemical reactions to how muscles move. To mesh that wild curiosity with scientific rigor, he used two strategies. First, he basically did natural selection among ideas. He tested his hunches against observations. The survivors stuck around, the losers got tossed. I do not know what I may appear to the world, but to myself I shall appear only as a boy playing on the seashore, amusing myself by occasionally finding a pebble more colorful than the ordinary, or a beautiful shell, while the great ocean of truth stretches out before me, unexplored. His second strategy was craftier. For ideas that looked promising but weren't fully proven, Newton sneaked them out in the form of questions. For instance, do not bodies act on light at a distance and bend its rays by this action? Now, for ages, people treated white as a symbol of purity. Think Egyptian priests' robes, modern bridal dresses. So they figured white sunlight had to be the purest thing around. But Newton dismantled that notion. Before him, people assumed white light got ruined as it passed through a prism, mixing with darkness to yield rainbow colors. Newton, however, showed that white light is actually a mixture of pure components. He did the defining experiment, shining light through two prisms. The first prism split white into the spectrum. The second could reassemble it, or isolate individual pure colors. Newton discovered these spectral colors couldn't be broken down further. They were the elements of light. This was the birth of the chemistry of light. Just as chemists isolate pure elements from matter, Newton isolated pure colors from light. The payoff wasn't just theoretical. Newton devised a new type of telescope, swapping out lenses for mirrors. But the real fireworks happened in the 19th century, when scientists spotted dark lines in the solar spectrum. Turned out each chemical element absorbs certain wavelengths, leaving a unique signature in the rainbow. This revolutionized how we see stars. Analyzing their light told us what they're made of. The discovery of helium is a fun example. During an 1868 solar eclipse, scientists spotted an unknown spectral line in the sun's corona, called it coronium, figuring it was some special solar element. Then, 27 years later, that same line turned up on Earth in uranium ore, and they realized this was helium, named after Helios, the sun god. So, analyzing light proved that stars and our Earth share the same elements. Before Isaac Newton shook the foundations of thought, giants like Galileo, Copernicus, and Kepler each chipped away at our comfy old worldview. Galileo aimed his scope at the moon and found mountains and craters just like Earth. Copernicus insisted Earth was a planet among many. Kepler nailed down the mathematical laws for planetary motion. But despite all these breakthroughs, people still pictured a gap between the heavens and the everyday. Kepler's laws described planetary orbits but didn't explain why they were that way, or how it all tied to the phenomena down here, in the mud. Then came Newton. In his major work, there's exactly one illustration, what Nobel laureate Frank Wilczek calls the most beautiful drawing in all scientific literature. It's simple at first glance, a tall mountain with lines showing the possible paths of a thrown stone. But behind this modest image hides a gargantuan idea. Imagine you're on top of this colossal mountain, chucking rocks. A weak toss drops at your feet. Throw harder, it lands farther away. But if you imagine throwing it outrageously hard, something mere mortals can't do, the rock stops falling altogether and starts orbiting the planet. Newton realized orbital motion is just a form of falling, except you're falling around the Earth so fast you keep missing it. The moon falls just like an apple, only it's whipping sideways at such a clip that it never smashes into us. That's a radical new view, a dynamic universe where one set of laws governs every movement, sky and earth united at last. Newton also added a fresh dimension to space, time. In his three-dimensional space-time, circular orbits become spirals. Time acts like a fourth dimension alongside length, width, and height. He saw curves as points sliding through time. That's how he invented calculus. At each instant, a planet tries to go straight at a constant speed, but a force yanks it off that path, forging a curve. Shove real planetary data into this method and bam! Newton discovered universal gravitation. With one mathematical rule, he explained the moon's motion, Earth's tides, our planet's shape, and the wandering arcs of comets. A single equation slicing through a tower of phenomena like butter. Later critics whined that Newton's so-called reductionism kills the wonder by oversimplifying nature. William Blake famously painted Newton as a mighty figure but ignoring the colorful world behind him, burying his nose in geometry. But does understanding really ruin beauty? Look at fractals, pure math making stunning images. Knowing the simple formulas behind the hypnotic patterns doesn't wreck their spell, it supercharges your admiration, if anything. Newton's laws let us predict the future and reconstruct the past. Plug in an object's position and velocity plus the forces acting on it, and you can figure out where it'll be at any moment. But there's a catch. You need a starting point, initial conditions. The equations alone can't do squat unless you give them a snapshot of reality at least once. It's like running a computer program. An algorithm is meaningless without input data. Maybe, as the philosopher Parmenides and later the physicist Hermann Weyl hinted, we need to see the world differently. Perhaps time is just how our minds parse reality, while the universe might exist as a single, timeless block. In that scenario, there's no beginning, no need for initial conditions, because the whole cosmic story is spread out in space-time all at once. Wild stuff indeed. Michael Faraday was born into poverty, the son of a London blacksmith. No fancy school for him. He worked as a bookbinder's apprentice and devoured science books in his downtime. He started attending public chemistry lectures by Humphrey Davy, taking such insanely detailed notes that Davy brought him on as an assistant. Faraday's math background, almost zero, just a dash of algebra and trigonometry. But that ended up being an advantage. Without rigid theories cluttering his brain, he relied on pure intuition and relentless experimentation. His biggest breakthrough? The idea of lines of force. Try his little experiment. Sprinkle iron filings on paper, then bring a magnet close. The filings magically align in these curved symmetrical lines. Other scientists just saw forces in a vacuum, but Faraday smelled something deeper. A special medium filling space, like air you can't see, but that blows clouds around. To the Newton fanboys of the era, this felt like stepping backward to invisible fluids. But one man was wowed by Faraday's vision, James Clerk Maxwell. Maxwell took Faraday's intuitive leaps and forged them into precise math. He imagined space teeming with vortex atoms, in which changes in electric fields generate magnetic fields and vice versa. Fields dancing in sync, fueling each other. His calculations showed these oscillations traveled at a specific speed, exactly the speed of light. So it dawned on them, light is the oscillation of this electromagnetic field. The combined insights of a self-taught bookbinder and a math-savvy professor birthed one of physics's all-time greatest theories, revealing that empty space is actually packed with electric and magnetic fields, swirling in an invisible ballet we call light. Faraday and Maxwell pictured the cosmos more like an intelligent spider might. Spiders sense reality through the quivers of their web. So, for them, it'd be no big shock that space is like a mesh of interlinked lines carrying forces and vibrations. Electromagnetic fields in plain English. When Maxwell set out to formalize this mathematically, he started with 4 known laws of electromagnetism, 2 from Gauss, 1 from Ampere, and 1 from Faraday. The resulting system was so elegant it practically begged to be drawn, but there was a snag. Imagine electric current streaming between 2 capacitor plates. By Ampere's law, that current should spawn a magnetic field, But in the gap between the plates, the current is zero. So, how could there still be a magnetic field? Maxwell's genius fix was a brand new fifth law. Changing electric fields must create magnetic fields, just like changing magnetic fields create electric fields. Bam! Contradiction resolved. Not only that, but the entire set of equations gained a dazzling symmetry and beauty. Note that Maxwell arrived at this fifth law not by some epic experiment, but at his desk, guided by the hunch that nature has symmetrical style. If a magnetic field can spawn an electric field, the reverse should also be true. Why wouldn't it be? With that stroke of brilliance, Maxwell's equations unlocked a vast realm of hidden waves, from radio signals to X-rays. Visible light turned out to be just one tiny slice of the mammoth electromagnetic spectrum. Maxwell's equations can be represented visually in the language of fluxes. In this form, they look like a kind of dance. I often mentally visualize them as a dance of concepts through space and time, and it's a real pleasure. Even at first glance, Maxwell's equations leave a sense of beauty and balance. Like the impact of more conventional art forms, this impression is easier to perceive than to explain. One cannot study this amazing theory without feeling as if the mathematical formulas have a life of their own, a mind of their own. It seems as if these formulas are smarter than we are, smarter even than the author himself. As if they give us more than was once put into them. Heinrich Hertz was the guy who ran the show to prove James Clerk Maxwell's ideas. It was Hertz who whipped up the earliest radio transmitters and receivers, making sense of radio waves. They're just light stretched out to a much longer wavelength and lower frequency. Think of it like electric and magnetic fields dancing more lazily through space. Moving from radio waves to shorter wavelength waves, we get microwave radiation, infrared rays, visible light, ultraviolet, X-rays, and gamma rays. Each of these many forms of light originates from a purely theoretical construct. In other words, the dream has spawned a fountain of modern technology. They are all in Maxwell's equations. Isn't that power? Maxwell's work didn't just rewrite physics, it changed how we look for fundamental laws. Instead of discovering laws first, then spotting symmetry, physicists started hunting for the most symmetric equations, assuming Mother Nature loves that kind of elegance. What do you know? It worked like a charm. Maxwell was also curious about how we see light. He noticed a quirk. The same color in our eyes might be totally different physically. Take yellow, for instance. Sometimes it's a pure rainbow color, sometimes it's just a blend of red and green. To your eye, those two yellows appear identical despite being physically distinct. Same goes for white. Sunshine's got all the rainbow in it, but you only need 3 colors, red, green, and blue, to conjure white. To study color perception, Maxwell built a simple but brilliant contraption. A spinning top with colored wedges. Twirl it, and the wedges blur into one color, exploiting how we see the world in snapshots, about every 0.4 seconds. Maxwell proved that any color we can perceive can be mixed from just 3 primaries, red, green, and blue, meaning the color space we sense is basically 3-dimensional. That insight didn't just clarify how we see color, it paved the way for modern TVs and smartphone screens. Meanwhile, the simplest light waves are pure spectral colors, with vibrations repeating at a constant interval. That interval's length equals color. Violet has a super teeny interval. Red's interval is roughly double that. Our visible rainbow only covers 1 octave. The wavelength changes by just a factor of 2. That's a teeny slice of what's possible. Electromagnetic waves can stretch anywhere from kilometers, radio, to teeny gamma rays. Our eyes snag only a small band precisely where the sun blasts the most light, but even in that narrow zone, we don't see everything. We only pick up 2 big slices of info: shape, spatial, and color, composition. It's like listening to a song but only hearing the rhythm and melody, missing all the layering. So what is color? Maxwell concluded. It's how we perceive the frequency of light waves. If you see spectral yellow, the electric and magnetic fields are oscillating at around 520 trillion times per second. Meanwhile, your eyes only serve up about 25 frames a second. Color is your brain's best way to keep tabs on these ultra-fast wobbles. But our color sense is limited. The complete color data of any light wave is infinite, because you'd have to measure intensity at every possible frequency. Our eyes squash that infinite info into just 3 numbers. In short, the space of color information is infinite dimensional, but we perceive as color only the three-dimensional surface onto which these infinite dimensions are projected. How does that happen? Our retinas host three types of light-absorbing molecules, one soaking up red best, another green, another blue. Light hits these molecules, they absorb photons, morph shape, and trigger electrical signals. The ratio of photons captured by each type sets the three numbers that define the color we see. This is how biology ties a neat bow on Maxwell's revelations. The infinite complexity of light meets the limited apparatus of our eyes, and out comes the vibrant show we call color. The light emitted by the sun and reaching us after interacting with a substance contains information about that substance, encoded in it by the latter's electrons. In simple terms, the color of objects encodes information about what they are made of. Color perception varies wildly among animals. Most mammals? Pretty lousy. Bulls see the world in grayscale. Yeah, that red cape is for the audience, not the bull. Dogs do slightly better, distinguishing two primary colors. Humans usually have three types of color receptors, although about 8% of men have color blindness and only get two. But the true heavyweight champions of color vision are mantis shrimp. These vicious marine predators pack 12 to 16 receptors each, letting them see visible light, UV, IR, and even polarization, handy for their sneaky crustacean communications. In the 20th century, physicists realized symmetry is the foundation of every natural law. As they built quantum theory, they found that understanding atoms required the same math that describes musical instruments. So they actually turned to Lord Rayleigh's theory of sound. That would have made Pythagoras grin from ear to ear. Look at a guitar's vibrating deck with its mesmerizing geometric patterns. Doesn't it echo the shapes of electron clouds in atoms? That's no accident. The same math ties them together. If Pythagoras' disciples had probed these vibrations more, maybe quantum mechanics would have shown up centuries earlier. The quantum world flips our usual rules on their head. In everyday life, a particle's got a location, but at the atomic level, it's smeared out like a probability cloud. The darker the cloud in some region, the higher the chance of finding the particle there. Behind that cloud lies the wave function, the true puppet master. You never directly see the wave function, but you can ask it questions like, where is the electron, or how fast is it moving? And it answers in probabilities. But here's the catch. Ask about position precisely and you lose clarity on velocity, and vice versa. Einstein tried to dodge this limitation but failed. Quantum reality demands multiple perspectives if you want the bigger picture. Take the simplest atom, hydrogen. It's basically a musical instrument. Schrödinger's equation for the electron parallels the equations for vibrating strings or membranes. A musical instrument has natural notes. The atom's got discrete states. In those states, the electron's probability cloud is fixed in some wild shape. Look at the pictures of these states. Complex, artistic patterns you'd think a human artist designed. If you peek at the wave functions themselves, it gets even more psychedelic. A swirling mandala of rainbow colors. Bertrand Russell once said math has a chilly, austere beauty like ancient sculpture. But Frank Wilczek says, sure, Schrödinger's equation is neat and precise, yet the images it produces are exuberant and alive. That's the magic of physics. Starkly simple equations unveiling a riotous tapestry of shapes. Even in hydrogen, the simplest of atoms. You see the blend of science and art. Plato was mostly right. Atoms truly do embody ideal forms. Matters built from identical particles that persist for billions of years. Maxwell thought this might be a signature of a creator's hand. Einstein famously asked, did God have any choice in creating the world? It sounds like old Greek philosophy, but at its core is a serious scientific notion. The universe must obey principles of beauty and symmetry. Look at Einstein's special relativity. He had two big ideas: Galileo's notion that physics laws are the same for everyone moving at a constant speed, and Maxwell's revelation that light's speed is a fundamental constant. But how can both hold true at once? In everyday life, if you sprint after something, you close the gap faster. Makes sense, right? Einstein found a totally unexpected fix for why light speed doesn't budge even if you're moving. Time itself morphs for different observers. What's pure time to you is partly space to me, and vice versa. That's the cosmic cheat code that keeps the speed of light locked. One weird implication is that color shifts if something zooms toward or away from you. Approaching objects look bluer, receding ones redder. Bottom line, all the colors of the rainbow are the same light, just glimpsed at different speeds. Newton once believed each color was unique, unchangeable, but in reality they're all facets of a single phenomenon. Welcome to the deeper unity of nature. Astronomers exploit this effect daily. Distant galaxies' redshift shows the universe is expanding. Score one more for Einstein's symmetry principle. But when Einstein tried merging Newton's gravity with special relativity, problems cropped up. In relativity, mass isn't even a fixed quantity. It can morph into energy. That nukes the idea of gravity as a mutual pull between lumps of mass. Einstein's cunning fix?
I gotta tell you, it was perfect.
He pictured space-time as a special fluid, the metric field, filling all of reality. Move at different speeds, you warp that field. The underlying physics is the same, but the field's shape changes. So the math says this field curves around matter, and matter in turn follows those curves. That's gravity, Einstein style. Just like Maxwell's photons carry electromagnetic forces, Einstein's gravitons carry the force of gravity. Meanwhile, the visible universe is assembled from a handful of building blocks: electrons, nuclei, and photons. So how do these simple components form the insane variety of matter we see? Look at electrons. They have three big desires. 1, they are drawn to positive nuclei but repel each other. 2, they prefer to spread out in smooth wave patterns called orbitals. And 3, they follow Pauli's rule: no more than 2 electrons per orbital. Take carbon with 6 electrons. 2 fill the innermost orbital, 2 go in a larger one, and the last 2 occupy those iconic dumbbell orbitals that can point in various directions. Crucially, those 4 outer electrons aren't super tightly bound, so when other atoms wander close, they can share electrons, forging chemical bonds. That's why carbon is king of molecular diversity, the bedrock of life on Earth. Its atoms can hook together in wild ways. In a diamond, each carbon pairs with 4 neighbors to make a flawless tetrahedron. The electrons lock down so tightly that diamond is nearly unbreakable and transparent. Let carbon bond with just 3 neighbors and you get a flat honeycomb of hexagons, better known as graphene. This single atom-thick material, a 2004 discovery using a pencil and Scotch tape, ended up bagging a Nobel Prize. Science is weird and glorious like that. Graphene is insanely strong yet feather-light. Legend says a 1 square meter graphene hammock could hold up a cat, but would weigh about as much as a single whisker, though no one's actually made such a thing yet. Stack sheets of graphene, and boom, graphite, the stuff in your pencil leads. Those layers slip across each other, so your scribbles flow easily. Once physicists nailed how atoms work, in the 20th century they uncovered 2 new fundamental forces, the strong and the weak. Both seemed to follow the same symmetry logic that governed electromagnetism, and presumably gravity too. So, is it possible that all natural forces are just different faces of one gorgeous overarching symmetry? We've seen how atoms are basically little musical instruments playing the tune of light. Let's dive deeper. Why do electrons, photons, and nuclei exist at all? Over the past century, physicists cooked up a theory that tries to answer that. The Standard Model. It's the blueprint that attempts to unify everything we see, electrons, quarks, bosons, you name it, into one big cosmic jam session. This commonplace phrase carries too much modesty. First, Standard Model smacks of common sense, with strong connotations, backwards thinking, and lack of imagination. Second, Standard Model sounds almost like a rule of thumb, suggestive of some kind of crude, hastily assembled construct. Neither of these smacks and hints should be associated with one of the greatest achievements, I would even say, the greatest achievement of human thought and effort. That is why I call it the main theory. The predictions of our big main theory have been confirmed with jaw-dropping precision. It underpins all natural sciences, cosmology, biology, you name it. But you won't find its beauty obvious at first glance. You've got to roll up your sleeves to see the elegance baked into its core. Basically, you have to treat particle properties as positions in certain spaces. Which might sound wild, but guess what? You're already doing it. Right now, every pixel on your screen is pinned by two coordinates, horizontal, vertical, and the color at that pixel is defined by three numbers, RGB. That's a property space, just like nature does it. Turns out color is a three-dimensional property space. And here's the kicker. The electromagnetic field, which carries light, can be thought of as a one-dimensional property space, kind of like the brightness slider for a single color channel. Meanwhile, the strong interaction that holds quarks together in nuclei uses a three-dimensional property space, and physicists actually call it color, even though it's got zilch to do with real color. The math is similar, so it's a neat example of how nature replays the same gorgeous theme across different levels of reality. It's like your phone's screen is a model of the physical world structure. Each fundamental particle sees other particles' properties as extra dimensions. Just like mixing a few primary colors can yield any shade, the interplay of these colored particles spawns the crazy variety of matter in our universe. Astrophysicist John Wheeler once summed up Einstein's gravity with a sledgehammer line. Matter tells space-time how to curve. Space-time tells matter how to move. Feels like yin and yang. Matter, yin, follows the path of least resistance, while space-time, yang, shapes that path. Modern physics shows the same duodynamic 4 times. Besides gravity, we've got electromagnetic, weak and strong interactions, each with a field tells matter how to move, matter tells field how to change. Partnership. Think 4 yin-yang couples dancing simultaneously in cosmic harmony. Each field is like a fluid saturating space, capable of ripples and flows. Light is waves in the electromagnetic fluid. Gravitational waves are pulses in space-time's fluid. This deep symmetry among all forces hints they're just facets of something unified beneath the surface. Nature loves reusing good ideas. In 1911, Rutherford's lab tested gold foil with alpha particles. Most zipped through the foil like it was air, implying atoms are mostly empty. But shockingly, some alpha particles bounced back, as if hitting a solid wall. Rutherford famously said it was like firing a heavy shell at tissue paper. He realized the only way that made sense is if nearly all the atom's mass was jammed into a tiny nucleus at the center, surrounded by a sprawling electron cloud, 100,000 times bigger than the nucleus itself. The nucleus, in turn, contained positively charged protons and neutral neutrons. But wait, positive charges repel each other, so why didn't the nucleus blow itself apart? There had to be a brand new force gluing it all together. Physicists started slamming protons together to crack that mystery, and got a carnival of new particles. Instead of neat collisions, they saw literal fireworks. Dozens of fresh hadrons popping out, living briefly before vanishing. Suddenly, there were hundreds of these strange beasts in the particle zoo. Researchers were going nuts. Robert Oppenheimer joked they should award the Nobel Prize to anyone who didn't discover a new particle that year. The subatomic world was wilder than they'd ever imagined. Enrico Fermi once quipped that if he'd known there'd be so many Greek-named particles, he would have become a botanist instead of a physicist. That's how insane things got in the mid-20th century. Researchers were practically drowning in elementary particles. The confusion was so epic that some experts started claiming maybe the human mind couldn't hack the subatomic world, like trying to teach a dog calculus. Enter Murray Gell-Mann and George Zweig, who finally brought order to the chaos. They propose that all these hadron particles are really built from smaller bits called quarks. Just 3 quark flavors can combine to generate the entire menagerie of hadrons. 3 quarks equals a baryon. Quark plus antiquark equals a meson. Simple, elegant. But also, why so many variations of quark combos? Because those quarks inside each hadron zip around with constant motion, each different dance forming a new particle. That left one big paradox. If quarks exist, why has nobody seen one? Why are protons and neutrons locked up so tight? Physicists dubbed this confinement. It sounded so bizarre that many refused to buy it. Then came a bombshell. The right equations for describing quarks were already out there, crafted by Yang and Mills a whopping 20 years earlier. These equations, based on local symmetry, nailed quark behavior. Frank Wilczek compares strong interaction to electromagnetism on steroids. Normal electromagnetism, you have one type of charge, electric, and one force carrier, the photon. But in the strong interaction, you have 3 types of color charge and 8 force carriers, gluons. Once powerful computers showed up, physicists tested the theory by letting them crunch the strong interaction equations. The results? Mind-blowing. For the first time, humans glimpsed the proton's internal structure in all its complicated glory. With just 3 inputs, the masses of 2 quark types and their interaction strength, scientists calculated all hadron masses, including the proton, with bullseye accuracy. Suddenly, a huge revelation slapped us in the face. Almost all the mass in ordinary matter arises from nothing. The proton's mass barely depends on the quark's own masses. It comes instead from the quark's frenetic motion and the energy of the gluon fields, courtesy of E=mc². Elegant math explaining the entire universe's baryonic mass. You and I are literally built from math made flesh. There's another key force, the weak interaction, letting protons morph into neutrons and vice versa. Without it, the sun wouldn't shine and earthbound life would be toast. On a deeper level, that transformation is a quark changing flavor and spitting out electrons plus antineutrinos. But only left-hand particles do this. That's weird as hell, so physicists guessed local symmetry might be at play again. Problem: the math said the weak force carriers ought to be massless, like photons. Observations, though, found them quite hefty. The fix was the same fluid trick again, but now with the Higgs field filling space. Like water slowing down light, the Higgs field slows certain particles, giving them mass. If that's true, then the field has to be made of some new particle, the Higgs boson. For decades, scientists scoured for this so-called God particle until 2012, when the Large Hadron Collider nailed it. That discovery was the crowning proof of a major theory. So why does anything exist at all? Where do electrons, photons, and atomic nuclei spring from? The Standard Model, symmetry, local fields, confinement, the Higgs. They're the puzzle pieces telling us how matter and forces are woven. Frank Wilczek says that behind everything we see lurk just a handful of fundamental fields obeying simple math laws, the so-called main theory. When these fields interact, they conjure what we call particles, electrons, photons, nuclei, etc. They're not separate objects at all, just ripples in these underlying fields, like waves on the ocean's surface. Everything around us springs from this cosmic field dance. So, is that the grand finale? Have we cracked nature's code and grasped the cosmos in all its glory? Nope.
Are you serious?
Not even close, says Wilczek. Why? Because our main theory only explains 4% of the universe's mass. The other 96% is made of dark matter and dark energy, 2 of the biggest mysteries in science. And we still don't know why there are 3 families of particles, or how the 4 fundamental forces ultimately connect. So don't buy the hype that we're one step away from a theory of everything. If there's some ultimate cosmic symmetry out there, we haven't pinned it down yet. The real question is, how much deeper does the rabbit hole go? We have open doors in front of us. Since we have essentially reached an understanding of what matter is, we are in the position of a child who has just learned the rules of chess, or a budding musician who has just figured out what sounds his instrument is capable of. Such elementary knowledge is a preparation for perfect mastery of art, but not yet art. Can we use imagination and computation, rather than trial and error, to design the materials of the future? Can we grasp what the universe is saying through the gravitational waves of neutrinos and axons? Can we comprehend the human mind molecule by molecule and systematically improve it? Can we develop quantum computers and use them to create truly alien forms of intelligence? To ask such questions is to discover in the maturity of one golden age the seeds of new ones. Symmetry is change without change. Mathematician Emmy Noether proved that any symmetry in nature's laws ties directly to the conservation of some physical quantity. Let's look at the deepest example. The laws of physics don't budge over time, yesterday, today, or 1,000 years from now. This so-called time-shift symmetry forces an astonishing conclusion. Energy doesn't just vanish or appear. People used to be clueless about that. Up till the mid-19th century, no one believed energy conservation was some unbreakable rule. Galileo first sniffed out a clue with swinging pendulums. Noticing changes in height matched changes in the square of velocity. Newton generalized it for particles, but only under ideal conditions. Then steam engine engineers realized energy never magically materializes. It morphs from one form to another. James Joule sealed the deal by turning a falling weight's mechanical energy into heat, making it crystal clear. But the why still loomed, until Noether strolled in, linking energy conservation to the simple, elegant fact that physics laws don't shift over time. That's why, if energy suddenly weren't conserved, we'd have to shred our basic beliefs about time and natural law. Noether's revelation went even deeper. She showed that when laws stay the same from place to place, space-shift symmetry, momentum is conserved. When laws don't care about directions, rotational symmetry, angular momentum is conserved. Kepler saw how momentum played out in planetary orbits, but Noether nailed the reason why. And speaking of why, you might wonder why we trust that laws of nature are consistent across all time and space. David Hume warned we can't be sure the sun will rise tomorrow. Bertrand Russell told of a chicken fed daily by the farmer until the day its neck got snapped. But we humans rely on interwoven observations and theories, not blind faith like that doomed chicken. Take the classic logic example. All men are mortal, Socrates is a man, so Socrates is mortal. That works not because we've tested every man's mortality, but because we get how the human body ages. Similarly, our conviction in unchanging physical laws isn't just repetitively seeing the sun pop up. Noether showed that energy's conservation is tied to time invariance, and checking distant galaxies tells us the same laws held billions of years ago too. Nature's all about standardized parts. Look at electrons. Every electron in the universe is exactly the same. That uniformity arises from quantum theory's structure itself. Apparently, the creator of nature was a fan of mass production, long before Henry Ford got the hint. Think back to a dodecahedron, one of those 5 perfect solids. If it's all taken apart, most folks won't recognize it. But if you know its shape, you see it straight off. 12 matching pentagons itching to snap into a single form. That's basically our situation with nature. The main theory in physics describes the entire world with a tiny set of equations explaining everything from chemistry and engineering to biology and the structure of stars. Probably not a huge amount of bullshit goes on there, but it still requires an efficient mind. There's a hidden, deep mathematical beauty and symmetry at its core. But peek closer and you'll spot flaws. It's got 4 separate interactions, even though it'd be cleaner to have one. It offers up 6 independent particle types, whereas we'd prefer something more unified. The 3 repeated families of particles and the existence of the Higgs field muck things up even further, like a master craftsman who left the job half-finished. Another possibility? Maybe there's an even deeper unity hiding underneath, like recognizing a dodecahedron from its broken edges. Maybe all these messy parts are just glimpses of a higher symmetry. Physicists turned to 19th century math rock stars like Sophus Lie and realized there are only a few candidates for such a unifying supersymmetry, much like there are only 5 Platonic solids. Then Howard Georgi and Sheldon Lee Glashow made a jaw-dropper discovery. One of those symmetries, SO10, operating in a 16-dimensional space, not only unifies the 3 fundamental interactions, but naturally includes all known matter particles. It's that aha moment when lines in the puzzle start to form a dodecahedron. A purely mathematical vision leads to an accurate portrait of the real world. Two different roads, empirical observation and abstract math, collide and produce the same result. That's the raw connection between math and how the universe is built. But this unified symmetry plan hit two snags. The first was that the theory predicted new particles, nicknamed mutatrons, that could mutate quarks into electrons. None had ever been seen. Luckily, the same Higgs field that hefts up the weak bosons could also inflate the masses of these mutatrons, making their effects vanish. Problem solved. The second snag was stickier. If all forces emerge from one mother symmetry, they should share the same strength. Yet the strong interaction is way more potent than the rest. And what about gravity? Your fridge magnet easily outmuscles Earth's gravity, so that doesn't sound too strong. But here's the kicker. The strong interaction gets weaker at smaller distances. So maybe if you zoom in super close, all forces converge to the same strength. That's where the vacuum's quantum jitters come in. It's not empty. There's a roiling ephemeral swirl of quantum fluids flipping so fast that across the distance of a human hair, the pattern changes trillions of time. Like water warping your view, these quantum froth distort reality on tiny scales. Once you factor that in, the forces nearly merge at a single point. Close, but not perfectly. Some said, well, that's the end of that. But the idea was too gorgeous to toss. Enter SUSY, also known as Supersymmetry. Discovered in 1974, it pairs up matter particles, electrons, quarks, with force particles, photons, gluons. SUSY claims these two categories are flip sides of one coin, introducing special quantum dimensions. One step in that dimension, and a matter particle transforms into a force particle, and vice versa. If this cosmic shape-shifting is real, it elegantly explains why matter and forces always show up together, like some yin and yang. In 1981, two physicists, Savas Dimopoulos and Frank Wilczek, collided at the Santa Barbara Institute. Dimopoulos was bursting with big unification dreams, while Wilczek was cautious, hunting for elegant simplicity. The problem with supersymmetry was that it predicted swarms of unknown particles we'd never spotted. So scientists hatched a sneaky plan to rescue the idea. Maybe supersymmetry's hidden from our eyes, broken in our everyday world. Meaning, the new particles might be so massive, we just can't produce them yet. Dimopoulos and Wilczek tried stacking up these broken supersymmetry models. One fix solved a problem but birthed another, and the models mushroomed into labyrinthine complexities. Finally, they ran a quick bare-bones calculation, hoping to show the approach was doomed so they could ditch it. Surprise! The simplistic calculation showed that supersymmetric theory could work just as well as the standard approach. That changed their game plan. Instead of explaining all the universe's details, they doubled down on one simple concept: using supersymmetry to unify all forces. Frank Wilczek put it this way: sometimes the most important step in understanding something is to realize that you shouldn't worry about everything in the world. It's usually better to be right about something specific than to have a not completely wrong theory about everything. Once physicists tossed supersymmetric effects into the equations, the three known forces, strong, weak, and electromagnetic, nailed the same unification point. A near-perfect sign they shared a single origin. Gravity, though, was way too weak to even appear on the same graph. It'd be off the page, beyond the visible cosmos. But gravity has a trick. It ramps up in strength crazy fast at high energies. Pushing that growth to unimaginably high energies, they found yet another miracle. Gravity also meets up with the other forces at that same point. We still don't know if supersymmetry is real. No experiment has uncovered those predicted superparticles. Each new search narrows the possibilities, and the more data we gather, the fewer hideouts they have. Maybe soon, we'll find out if nature actually paves a road to cosmic oneness. Not every pretty idea proves true. Plato believed in perfect geometric atoms. Kepler chased perfect orbits in the solar system. Leonardo saw geometry in the human form. All were wrong. Meanwhile, not all truths are gorgeous. Our main theory has lumps. tangled particle masses, shadowy dark matter, and dark energy. Even if grand unification is validated, those puzzles won't vanish. But look how far we've soared anyway. Reality's overshadowed even our ancestors' craziest fantasies. We discovered music in atoms and the vacuum. Not Pythagoras' music of the spheres, but something just as enthralling. Kepler bombed with geometry of orbits, yet he nailed the precise orbital laws. Our microwave sky glimpses the early universe 13.8 billion years ago. Everything was nearly uniform, with minuscule inhomogeneities of a few 10,000ths. From those meager fluctuations, entire galaxies, stars, and planets emerged, likely from quantum ripples in the microcosm. So the loop between tiniest and largest is shut. We humans sit smack in the middle of this epic connection, big enough to dissect atoms, small enough to eye galaxies. The world is both starkly simple and fiendishly intricate. Its core is built on neat laws and symmetries, yet births endless complexity. Earth is a speck in the cosmic ocean, but our speck is where all human history plays out. We're just quarks and electrons, yet we can think and choose. Embracing both sides, that's real wisdom. As Wilczek wraps up, we humans balance between the microcosm and the macrocosm, contain the former, perceive the latter, and comprehend both.